If Earth were flat, you would not need a government document, a satellite photograph, or a scientist in a white coat to prove otherwise. A flat Earth would have to behave like a flat object. Light would travel across it in certain ways. Distant objects would disappear in certain ways. The stars would move in certain ways. Shadows would line up in certain ways. And when you compare those predictions with what people can measure for themselves, the flat model starts failing again and again. One small correction first. Earth is not a perfect ball. It is slightly wider around the equator than from pole to pole, and its surface is full of mountains, trenches, and small variations in gravity. Noah describes the basic shape as an irregular ellipsoid. For everyday purposes, though, round Earth means a globe rather than a flat disk. And there are many independent ways to test that. The first one is almost embarrassingly ordinary. Watch a ship move away from shore. It does not simply become a smaller and smaller complete ship until it turns into a dot. The lowest part disappears first. The hull goes, then more of the structure, while the highest parts remain visible longer. Aristotle mentioned this more than 2,000 years ago, and you can still test it today with a harbor, a long lake, or a coastline. A zoom lens helps with resolution, but it does not bring the hidden hull back once it has dropped below the geometric horizon. That distinction matters. If the ship were merely too small to see, enough optical zoom should restore the entire object. Instead, part of it is blocked by the curved surface between you and the ship. Move your camera higher, and you can see farther. Go back down close to the water and the horizon comes closer again. No NASA required. A tripod, a long lens, and a boring afternoon near the coast are enough. The second test is written across the night sky. In the northern hemisphere, the altitude of Polaris, the North Star, is approximately equal to your latitude. Near the North Pole, Polaris sits almost overhead. Move south, and it appears lower. Near the equator, it is close to the horizon, and farther into the southern hemisphere, it disappears from view. Noah's own material on astronomical positioning notes that measuring the elevation of Polaris is one of the simplest ways to estimate latitude in the northern hemisphere. That sounds like an old navigation trick, because it is. Sailors used the sky long before GPS, and there is an extra problem for a flat map. Different constellations become visible as you travel north or south. Some southern stars cannot be seen from much of Europe or North America at all. Meanwhile, observers in the southern hemisphere see stars circling a southern celestial pole. The pattern changes smoothly with latitude, exactly as you would expect when people stand on different parts of a globe. Take two friends, one in northern Europe and one in southern Australia, and have them make long exposure photographs of star trails. The circles form around different celestial poles. The apparent direction of rotation is opposite around the north and south poles. A single flat surface with everyone facing the same up has a difficult time reproducing all of those observations at once without inventing a separate rule for each location. The third piece of evidence appears during a lunar eclipse. When the moon passes into Earth's shadow, the edge of that shadow is curved. NASA notes that people were using this observation in antiquity. Aristotle specifically argued that Earth must be spherical because its shadow on the moon remains round during lunar eclipses. A coin can cast a circular shadow, of course, but only when it is oriented the right way. Tilt it, and the shadow becomes an ellipse, then a thin line. A sphere is different. Viewed from any direction, its silhouette remains a circle. Lunar eclipses happen with different geometries and at different positions in the sky, yet the Earth's umbral shadow crossing the moon stays round. You can watch this yourself. No image processing, no fisheye lens. Just the moon slowly entering a curved shadow. The fourth test is one of the best because you can reproduce a version of it with two sticks. Around 240 BC, Eratosthenes compared the sun's angle in two Egyptian cities. At Syene, near modern Aswan, the midday sun around the summer solstice was essentially overhead. In Alexandria, a vertical object cast a measurable shadow. The angular difference was about 7.2 degrees, close to 1/50th of a full circle. If the sun is far enough away that its rays arrive almost parallel, that angle tells you the curvature between the two locations. Eratosthenes combined the angle with the distance between the cities and estimated Earth's circumference. The American Physical Society describes the method and notes that, despite imperfect ancient distance measurements and simplifying assumptions, the result was remarkably close to the modern value of roughly 40,000 kilometers. And you can do the same experiment today with a friend hundreds of kilometers north or south of you. Put vertical sticks on level ground, measure the shadows at local solar noon, compare the angles, and use the distance between the locations. Schools have repeated versions of this experiment many times. You are not assuming a globe just because someone told you to. You are measuring curvature from geometry. The fifth test hides inside something as ordinary as a route planner. People have measured distances between ports, cities, islands, and survey markers for centuries. On a globe, the shortest long-distance paths follow great circles, which is why an airline route can look bent on a rectangular world map, even though the aircraft is taking an efficient path across the curved surface. Now try to make one flat map that preserves all those measured distances. A common flat Earth map puts the North Pole in the center and spreads the southern hemisphere around the outside. That creates a huge problem. Southern distances become badly stretched. Distances among places such as South America, Southern Africa, Australia, and New Zealand cannot all match reality at the same time, while northern distances also remain correct. You can redraw the flat map, sure, but fixing one region breaks another. A globe handles the same network with one geometry. Mariners, surveyors, and modern navigation systems all use that geometry because the distances close properly. The sixth test looks less dramatic. A heavy metal ball swinging on a long cable in a museum. It is the Foucault Pendulum. Léon Foucault used the experiment in 1851 to demonstrate Earth's rotation without relying on astronomical observations. The Smithsonian explains the basic idea. The pendulum tends to keep swinging in the same plane while Earth rotates underneath it. Here is the useful detail. The apparent rate at which that swing direction turns depends on latitude. At the North Pole, it would complete one turn in roughly a day. The effect becomes slower as you move toward the equator, reaches zero at the equator in the idealized case, and reverses in the southern hemisphere. That latitude dependence is exactly what a rotating globe predicts. A rigid flat disk does not naturally give observers at different north-south locations that same pattern. You can see this in a boring way too. Universities and science museums around the world operate Foucault pendulums. They do not need to exchange a secret signal every morning telling the pendulum which way to drift. The effect comes from mechanics, latitude, and Earth's rotation. The seventh piece is Modern Geodesy. And this one is enormous because it is not a single photograph or a single agency. Geodesy is the science of precisely measuring Earth's shape, orientation, and gravity field. NOAA's National Geodetic Survey uses an ellipsoid as the basic mathematical model and a more detailed geoid when gravity and mean sea level matter. GPS measurements, surveying networks, satellite orbits, mapping, navigation, and engineering all depend on these models being accurate. If Earth were flat, the arrow would not stay hidden in a textbook. Coordinates would drift. Long-distance surveying would fail to close. Satellite predictions would break. Aircraft and ships using independent navigation systems would accumulate huge position errors. Engineers in different countries would discover that the same supposedly global coordinate system stopped matching physical locations. Instead, geodesists can measure subtle details beyond simple round versus flat. They detect that Earth is slightly flattened at the poles and bulges at the equator. They model small variations in the gravity field. NASA has used satellite laser ranging for decades to make extremely precise measurements of Earth's shape and rotation. We are far past asking whether the surface is a plane. The measurements are sensitive enough to study tiny deviations from an ideal sphere. And that is the part that gets lost in flat Earth arguments. There is no single piece of evidence you must trust. You do not have to begin with a space photograph. Start with a ship, then look at Polaris. Watch a lunar eclipse. Compare two shadows. Measure how the horizon changes with height. Visit a Foucault pendulum. Then look at what GPS and geodesy have to predict correctly every day. Any one observation can invite an excuse. Perspective, lenses, refraction, a bad measurement, a suspicious institution. Fine. But the explanations have to work together. The same model has to explain the horizon, the stars, the eclipses, the shadows, rotation, navigation, and precision surveying without changing its rules from one experiment to the next. A globe does that. A flat Earth does not. And the strongest evidence is not that somebody once took a famous picture from space. It is that thousands of ordinary observations, old experiments, modern instruments, and practical systems all keep measuring the same curved world.
Thanks for watching! If you enjoyed the video, please like, subscribe, and leave a comment below. See you in the next one!